Hello, and thank you for watching the Physics Lab 5. We'll be doing the human rocket. So the purpose is to demonstrate the effect of drag on free fall and create an accurate equation of drag. I will be modeling Felix Baumgartner's fall from space. The model is Felix Baumgartner's space jump, and this is him. And here's the other model is the VPython simulation that I coded. So here's that little yellow dot that falls down. And he significantly slows down as he goes through it. But he reaches a pretty quick speed that is faster than the speed of sound. The speed of sound is 330 meters per second. Alright, so fundamental physics principles: force of gravity, Fg, generally the mass times gravity. Force of drag as a function of altitude is going to be 1/2 times the pressure times velocity squared times a drag constant times area. Cross-sectional area. So pressure as a function of altitude is going to be this big equation, and I'll list off like what these constants are in just a second. So the main result preview is that his estimated real maximum speed was around 377 meters per second. My simulated was 898 meters per second. And however, that was his maximum. His final speed without a parachute was when he hit the ground technically in the simulation was 42. So some assumptions: that he is a perfect ellipsoid. Obviously he is not, but that I modeled it in Desmos 3D graphing, what the ellipsoid that I programmed into would look like. I assume that he's about a meter wide, and that he's only like a 1/2 meter thickness across his chest, and that he's about 2 meters tall with the whole spacesuit. His mass from the website was 73 kilograms. Felix does not turn or deform in the air. His initial height was 38,969 meters. His landing spot altitude, I said, was 1,089 meters above sea level because he landed near Roswell, New Mexico. And when I looked up Roswell, New Mexico's altitude, that was the answer. So standard atmospheric pressure at sea level, P naught. This is all the constants that were in the previous equation. Is that we have molar mass of dry air, universal gas constant. That's pretty common in chemistry. Standard temperature at sea level, temperature lapse rate. So that's going to be how much it changes depending on the altitude. Acceleration due to gravity, 9.8 meters per second, pretty standard. And so when I looked up what the drag coefficient of an ellipsoid typically is, I was told that it was between 0.1 and 0.3. I took the higher end of that because there's a lot of error, and he's not a perfect ellipsoid, so he's probably going to have more drag generally. So I went with 0.3. Obviously the system is Felix jumping, and his surroundings are the atmosphere and Earth. Initial conditions: Felix's velocity is 0 meters per second. His position, I just said only in the x direction, or only in the y direction at the maximum altitude. So here's the coding. I set the scene at first to make a little ground. That's what that box is. I programmed the ellipsoid, his mass, his velocity. I create a little curve to follow him. I set the rate really high because it would take a long time if I didn't. And then I program in his the force of gravity, which is pretty simple, but then I have to go through the force of drag. And the hardest part about this is just getting the pressure, and that is that long, like line 28. And then as we keep going through it, the force of drag is finally calculated, and then use position update formula. And use FNet is going to be Fg plus Fd. That's the only forces that are acting on him at this point. And then update his position with the V final because it is a non-constant force. Let me iterate this. So similarities and differences. In actual versus in simulated, max speed was only 5 meters per second. I say that's pretty accurate. Felix is nowhere close to being a perfect ellipsoid. He is a man in a spacesuit, and that is just not anywhere close to being perfectly elliptical. Or ellipsoidal. Felix also began to spin in the air, and at the end he deployed a parachute just to slow his fall. In reality, what if there were no drag? I just took out Fd from the equation, or from the coding, force of drag, and his max velocity at the end of this was 852.6 meters per second, and he fell very quickly. You can tell immediately how much faster that simulation went. What does it mean? Why does Felix slowed down when incorporating air resistance? So at the end, his maximum speed was around 380 meters per second, but he hit the ground in the simulation at around 40 meters per second. So pressure increases as altitude decreases. So when he gets closer to the surface of the Earth, it's going to increase the drag, the force of drag, and the force of drag increases exponentially as velocity increases. It is proportional to Fd is proportional to v squared. So any bit that velocity goes up, the force of drag is going to increase exponentially. This is why he slows down to such a great degree. Thank you for watching. I hope you have a great day.